Hi guys, it's your science teacher here, back with another video. This time I'm going to go through the whole of chemistry paper 1, which sounds like a lot, but I'm going to try and keep it as concise as possible. If you want to watch some content in more depth, please go to my playlists and watch the individual topic videos. But now it is time to get straight into it, so make sure you've got a pen and paper ready and let's get started. Let's start off the video by looking at what atoms are and how we can represent atoms. So atoms are the building blocks of all matter. And in chemistry, we need to know actually the 3 subatomic particles that make up atoms. And the first one can be found in the center part of my atom, which is known as the nucleus. And they have a positive charge and they are called protons. It's quite easy to remember them because P for positive. Also in the center part of my atom, I also have a neutral subatomic particle, and a neutral subatomic particle is called a neutron. And finally, around the outside of my nucleus, in what are called shells or orbitals, I have my last subatomic particle, which are called electrons. And they are found in shells. And this center part of the atom, can you remember what it was called? Yes, that was the nucleus. Now, a key thing about our atom is most of the mass is centered in that nucleus. So the only things that have mass in my atom are protons and neutrons. Electrons do have mass, but it's incredibly tiny. The electron's mass is equal to 1 over 2,000. And these units, because I know scientists like units, it's atomic mass units. Their charges are dead easy to remember because protons positive, neutrons are neutral, and electrons, their charge must balance out the positive charge of the protons, so they have a charge of -1. Now we know what atoms are and what they are made of, we can actually create some atoms. If you find an atom in the periodic table, for example lithium, you will see that it is accompanied by a couple of numbers. But what do these numbers actually represent? Luckily, the periodic table does come with a key, and even in your exam you will get this key, and it says that the bottom number is known as my atomic number and the top number is called the atomic. But how do I use these numbers to create an atom? Well, the bottom number, the atomic number, tells us how many protons are in the nucleus, and that is why the atomic number is sometimes called the proton number. The top number is called the atomic mass, and this means because the protons and neutrons are the only things in the atom that have a considerable mass, the top number tells us the number of protons added to the number of neutrons. Now we already know the number of protons in my lithium atom because that's 3, it's the bottom number. So I can simply work out the number of neutrons by doing the mass minus the atomic number. So let's do that for lithium now. Lithium will have 3 protons, and we can tell that by the bottom number. Now, if I do the top number minus the bottom number, that tells me that it has 4 neutrons. And then the last thing to work out is how many electrons it will have. Now, if you remember back to the previous slide, protons had a positive charge and electrons had a negative charge. In an atom, the charges always cancel each other out. So lithium has 3 protons, so lithium must also have 3 electrons in its atom. We can actually draw out an electron configuration of lithium too, which is needed for our GCSEs. And the way we do that is by following a rule, and that rule for drawing out these atoms is called the 2-8. And the 2-8-8 rule just simply states how many electrons can go in each shell. So for lithium, it's really simple. Because it only has 3 electrons, there will be 2 in the first shell, and there will be 1 more shell, and that will only have 1 electron in. Now you can always check these as well because of the fact lithium is in group 1, and that means that it'll have 1 electron in its outer shell. And lithium is in period 2, and that means it will have 2 electron orbitals. Let's try one more example. Here I have an atom of magnesium, which has the numbers 12 and 24. If I'm to draw its electron configuration, I first must need to know how many electrons are inside the atom, and that is simply just the atomic number. So, magnesium is going to have 12 electrons. 2 electrons can go in my first shell. 8 electrons can go in my second shell. I like to fill up my shells following a north, east, south, west approach. And then finally, if I count how many electrons I've drawn so far, I can work out how many are left. I've so far drawn 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 2 more electrons to draw. So 1 more shell. And there we go. That is an atom of magnesium. So we looked at how to draw the electron configuration of atoms. However, atoms usually like to gain or lose electrons to become more stable. So we said that they could have the 2-8-8 configuration. Well, all atoms want to have a full outer shell, and they do this by losing or gaining electrons. And we say that it is an ion when an atom has lost or gained electron to become more stable. Now, metals always lose electrons because it is easier for them to lose than gain electrons. So let's pick a metal. Let's pick beryllium. And if I draw out the electron configuration of a beryllium atom, then I would have 2 electrons in my first shell and 2 in my outer shell. Because it's in group 2, remember, you can just check it's in group 2, so it's got 2 electrons in its outer shell. Now, there is 2 ways beryllium could have a full outer shell. It could either gain 6 or lose 2. And atoms always do what's easiest for them. So beryllium's going to lose 2 electrons. And I draw a bracket around to show that it's become an ion. And it now only has 1 shell. It's lost 2 electrons. It's much happier like this. It's more stable. So it now has a charge of 2+. The reason for this positive charge is because of the fact it now has more protons in its nucleus than it has electrons in its orbitals. Remember, electrons are negatively charged and protons are positively charged. Now this beryllium ion has 4 protons but only 2 electrons. Let's look at drawing the ion of a non-metal now. So let's look at fluorine. Fluorine is a non-metal. And fluorine has 9 electrons as a atom. So let's draw that out first. It's in group 7. It's a halogen. So it's going to have 7 electrons in its outer shell. Let's draw them 2 in its inner shell as well. Very sloppy from me. There we go. And that is fluorine drawn out. Now, fluorine could do 2 things to become an ion. It could either lose 7 or gain 1. And as you probably know, gaining one sounds a lot easier, so that's what fluorine is going to do. And once it has gained one, it's now called a fluoride ion, and it's really easy with non-metals to name them. Once they have gained them electrons, you just change the ending from "-ine" to "-ide". So that's all you have to do. Now I've drawn it, let's work out the charge that it's going to have. It's gained one. It now has 10 electrons, but it only has 9 neutrons. So it's going to have one extra negative charge, so it's going to have the charge -1. A really easy way to remember whether you've got positive or negative charged ions is by thinking of electrons like naughty children in a classroom. If the teacher loses them naughty children, he's going to be positive, and if he gains extra naughty children into the classroom, he's very negative. So we've looked at atoms, we've looked at ions, now we're going to look at something called isotopes, which is another key definition we need to know at the start of the chemistry syllabus. The reason for it is because it explains some strange occurrences that we can see in the periodic table. Here we have chlorine, and chlorine have the numbers, the atomic number of 17, and atomic mass of 35.5. But how can this be, as you can't have half a subatomic particle? You can't have 17 protons, 17 electrons, and then have 17 and then have 18.5 neutrons. It doesn't work like that. So how have we ended up with this in the periodic table? Well, the reason is because of the fact chlorine has 2 main isotopes. These are atoms that have the same number of protons and electrons, but a different number of neutrons. So chlorine is made up of the 2 isotopes, chlorine 35 and chlorine 37. So chlorine here both times has 17 protons, 17 electrons. However, over here it has 18 neutrons, and over here it has 20 neutrons. So what you're seeing over here with this atomic mass is it's in fact an average atomic mass. So from this, you can probably work out which one is more abundant. That means which one there is more of. There is more chlorine 35 in a sample of chlorine because it's 35.5 on the periodic table. In fact, it is in a 4-to-1 ratio. Every time you have 4 chlorine 35s, you only have 1 chlorine 37 isotope. So the key to an isotope is that you have the same atomic number but a different atomic mass. When we only have one atom present, we can say that we have an element. So here you can see both of my atoms are the same. They are bonded to one another, meaning that it's a diatomic element, but it is an element nonetheless because there is only one type of atom present there. I've made sure that they're both relatively the same size and they are clearly the same colour. So this shows an element, and it doesn't matter how them elements are together, but we could also say that this is a pure substance as well because there's only one element or compound in there. This is also a pure substance here, but you can see that there's 2 elements clearly in there. Let's say for just ease of mind that this green atom is hydrogen, and this red one is, and this red atom is oxygen. Well, here you can see that they're bonded together, and therefore they've made something called a compound, which is just one or more atoms chemically bonded. However, most things in life don't come pure. Often we find many different things inside a substance, and we call these things mixtures. And here you can see that I've got some of that hydrogen. It's mixed in with the water. That's like what goes on in the air that we breathe around us. That's a mixture of many different gases. There is some water, hydrogen, nitrogen, oxygen, carbon dioxide, all that good stuff. And this is where we have one or more elements or compounds, and they're not chemically bonded. Because they're not bonded, they can be separated, and that's what we're going to look at now. So there are different ways that you can use in order to separate mixtures, and it's all about choosing the most appropriate method. The first one we're going to look at is distillation, which is usually used to separate two liquids. And what is so important about these liquids is they must have different boiling points for it to work. An example could be ethanol and water, or ink and water. Now, water has quite a low boiling point, so if it was ink and water inside there, what would happen would be the water would evaporate, go up here and go down into what is called a condenser. And in this condenser, the water would turn back from a gas into a liquid before being collected down here. If we want to separate a salt that is dissolved in a liquid, so what we call a soluble salt, we can use a technique called crystallization. And the way that crystallization works is your liquid gets evaporated off and it just leaves behind the salt that you started with. And then the final method here is chromatography, and chromatography works by separating mixtures which have a different solubility. So they are often liquids again, but here if we look at this chromatogram, that's what it's called. You have the stationary phase, which is the paper, and it looks like you've got food dyes that are moving up the chromatography paper, and the ones that stay at the bottom have the least solubility, and the ones that travel furthest up the chromatography paper have the highest solubility. So depending on what mixture you have at the start controls which method of separation you use. We are doing amazing so far, and we are going to move on to the next topic now, which is the periodic table. And we are going to look at how this periodic table was designed first. And the first key player was a man called John Newland. And what John Newland did was he noticed that every 8 elements, a kind of pattern started to emerge, and they reacted very similarly. Every 8 elements going up in atomic mass. He did, however, make a few glaring errors. Probably you can notice a few just looking. He put a few elements in the same box. This cannot happen in a periodic table. These do not have the same atomic mass, and they shouldn't be put in the same box. Also, he put things with different reactivity in the same group. So here we've got copper, which is an incredibly unreactive transition metal, and that's been put in the same group as lithium, sodium, and potassium, which is in group 1. And these are incredibly reactive metals, alkali metals. Also, you probably can see that he's missing quite a lot of elements from this law of octaves to the modern periodic table, which is down here. And that's because of the fact that there was a lot of undiscovered elements at the time. I know we can't have a go at him for that. However, there was one scientist who did find a way around this, and his name was Dmitry Mendeleev. And he was a Russian chemist. And what he did, which was so amazing at the time, was he left gaps for undiscovered elements. And the reason why other scientists got on board with his version of the periodic table was because of the fact he could predict the properties of elements that were undiscovered. Yes, you heard me right. He could predict what an element would be like even before it was undiscovered because of its position in the periodic table. He noticed that elements that were in the same group reacted very similarly. So let's have a look at this periodic table now and look at a few terms which will help us describe it. The first one is groups, and groups are what go down in the periodic table. So we have group 1 over here, 2 over here, and then we say 3, 4, 5, 6, 7, and this last one can be called group A or group 0. For the purpose of this, we are going to ignore this middle block, which is called the transition metals, and we don't include them in our groups for GCSE. And the reason why elements in the same group react similarly is because of the fact they have the same number of electrons in the outer shell. Elements that are in group 1 will have 1 electron in their outer shell. Elements in group 7 will have 7 electrons in their outer shell. As well as groups going down, we also have periods going across. So we have period 1 with hydrogen and helium, and then we have period 2 with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Now we need to know about a few key groups. For example, we need to know about group 1, which are called the alkaline metals, group 7, which are the halogens, and group 8 or 0, which are called the noble gases. So let's have a look at them. Okay, so let's first look at group 1 in the periodic table. That's a nice place to start, isn't it? Which is called the alkali metals. And these metals are incredibly cool because they are so reactive. And the reason why they are so reactive is because they have 1 electron in their outer shell. For example, let's look at lithium. If I was to draw out lithium, I've already done it before, but let's just do it again. It only has 1 electron in its outer shell, and it reacts by losing that electron. And because it's only got 1 electron to lose, these react really quickly and really violently. And it gets more reactive as we go down the group. So we've looked at lithium, but it actually gets more reactive all the way as we go down the group. Other cool things about group 1 is that they are very shiny, and also they are soft and easy to cut. Probably your teachers did that. Here is actually a vial containing some alkaline metals inside it. They have to be stored in oil because of the fact they are so reactive, and you probably saw in a lab them reacting with water. And when they do that, what happens is you make the metal hydroxide, and you also make hydrogen gas. When your teacher dropped them all in water, what you probably saw was lithium started to fizz, sodium fizzed a bit more vigorously, and potassium even more vigorously. Sometimes you even get to observe that beautiful lilac flame with potassium when you react it with water. If you did manage to get to see rubidium in the lab, that's incredibly cool. And if you saw maybe on YouTube, you could Google cesium and francium with water, because they are very vigorous reactions. But why do they get more reactive going down the group? Well, that is all to do with a property called shielding. So I drew out the electrical configuration of lithium, but if I do sodium up here, what you notice about sodium compared to lithium is it has 1 more shell. That means the electron, that outer electron, is 1 shell further away from that positive nucleus. And these electrons are attracted to that positive nucleus. Think there's positive protons inside that nucleus, there's negative electrons. Oppositely charged things attract one another. And there's more shielding between them. That's what these orbitals do. They shield that nucleus. So therefore, it's easier for sodium to lose an electron than lithium. That is why sodium is more reactive. And that property is called shielding. Let's look at another really cool group now, and that is the halogens, which are in group 7. And they all, of course, will have 7 electrons in their outer shell. I've drawn fluorine before, but let's just draw it out again. And we'll also draw chlorine next to it as well. So the key difference between fluorine and chlorine is just the fact that chlorine is going to have 1 more shell, just like with the last example, which we looked at with lithium and sodium. But because they are in group 7, they have 7 electrons in their outer shell. With the group 1 alkali metals, we observed that they got more reactive down the group. But the opposite is observed with the halogens. These are still incredibly reactive substances. These are non-metals, though, this time. They get more reactive up the group. So fluorine is the most reactive halogen. And the same logic can be applied, that shielding logic that we've looked at before. If we look at the 2 electron configurations, fluorine has 1 less shell, and the way it's going to react is by gaining an electron, and it's more easy for fluorine to gain that electron because of the fact the nucleus is closer to the outer shell, so it's easier for it to attract in an electron. A cool thing you can do with halogens is you can react them together. So you can react a metal halide with another halogen and observe something called a displacement reaction. I'll show you what I mean by that now. Say, for example, if you had potassium iodide and you reacted that with fluorine, what you would observe is because fluorine is more reactive, it steals the potassium away from the iodine, and you would end up making potassium fluoride, and you'd also make some iodine. And these reactions are known as displacement reactions, and they'll only happen if the halogen you are trying to react in to displace is more reactive than the halogen bonded to that metal. Other cool things about group 7 is they are incredibly toxic non-metals, and also they get more dense down the group. So they get more reactive up the group, but they get more dense down the group. And in fact, you can observe this. This is a vial of fluorine, which is a gas. And if you go down the group, once you go to bromine, you have a liquid. And then if you keep going, iodine's in fact a solid. So is astatine as well below it. And they get more dark as well down the group. So they get more dark and dense as well. Fluorine is a yellowy gas, and chlorine's green. Bromine is a browny orange color, and then you get into black solids. There's one more group that you could be asked about, and that is group 0, or sometimes called group 8. And these are the noble gases. And the reason why you learn about them is because, in fact, they're incredibly boring. And that's what makes them really useful, is the fact that they are so unreactive, they are so stable that they are incredibly useful in a lot of processes. The reason why they are so stable is because they have a full outer shell of electrons. This is neon, for example, and it took a long time for these noble gases to be discovered because of the fact they can go unnoticed because they're so stable and they won't react with other things. Argon is in the air, for example, and it took a long time for it to be discovered. Also, this center of the periodic table, you need to know its name. You don't have to know much about them because they're quite unreactive as well. These are the transition metals. You don't need to know much about them. You just need to know that they're there in the periodic table and they make up the middle section. They're quite unreactive. They're not like the group 1 or group 2 metals. They're unreactive as well. They're often used for making catalysts. We've now looked at group 1 and we've looked at group 7, but what would happen if you took a group 1 alkali metal and you reacted it with a group 7 halogen? Well, let's actually look at what would happen. So let's take sodium, for example, which is in group 1, and we'll draw out the electron configuration of sodium. And this is called a dot and cross diagram because I'm going to draw sodium with crosses and I'm going to draw chlorine with dots. And let's look at chlorine then. Chlorine I'll draw with dots. Chlorine has 17 electrons, so let's get them all drawn out. It's going to have 7 in the outer shell. And if I look at the electron configurations of sodium and I look at chlorine, sodium needs to lose 1 electron and chlorine needs to gain 1 electron. This is very convenient, isn't it? And the way that they can do that is by bonding with one another in what is called a ionic bond. And an ionic bond happens between any metal and non-metal. Alright, so let's have a look at what happens when the sodium loses its electron. So sodium's going to lose 1 electron, and when it loses that electron, you guessed right, it's going to have a positive charge, isn't it? Just like we did about with the ions, and the chlorine is going to gain 1 electron, and now that's going to be called chloride, and it gets that electron from the sodium, and you can show that by putting the cross in for that. You actually only need to draw the outer shell for these diagrams, but because I've drawn all the shells, I will draw in the extra electrons. And the chlorine has gone from being neutrally charged to now being chloride, so it has -1 charge. It doesn't always have to be as convenient as with sodium chloride here, which is bonded together. And if I was to draw them out next to each other, it would look like this, Na. If I was just drawing the outer shell, it would look like this with chloride. Doesn't always have to be like this. Sometimes we can get more difficult examples. For example, if I had a group 3 metal like aluminium, that would lose 3 electrons. It would lose its 3 outer shell and it would have a 3+ charge. And if that was to bond with chlorine, well, aluminium needs to lose 3 and chlorine only needs to gain 1. So the way we get around that situation is the fact that there would be 3 chlorines for every 1 aluminium. And I can represent that by just putting a little 3 here. All I'm saying here is the charges need to always balance out. And you can use what's sometimes called the diagonal rule in order to work out how many of each species you have. So you're going to have 1 aluminium and 3 chlorines. Alright, now let's look at some of the cool properties of these ionic compounds. This is, in fact, sodium chloride, and you can tell that from the ratio 1:1 of them sodium and chloride ions in there. And this makes up what is called a giant ionic lattice. And that just basically means a large repeating structure. And these ionic compounds have some great properties. They will conduct electricity when molten or in water. This is because the ions are free to move around. They can't conduct in a solid, but they can when they are free to move around. Also, they have incredibly high melting and boiling points because of the fact that they have strong electrostatic forces. This basically means that the positive charges and the negative charges attract each other really strongly, and this means that it takes a lot of force to break this electrostatic attraction, and it has a high melting point and boiling point. We've looked at what happens if we have a metal bonding with a non-metal, but what happens when you have 2 non-metals? Well, what you get instead is something called a covalent bond. And unlike with ionic bonds where the electrons are actually donated, the electrons are shared inside a covalent bond. Now, The atom still wants to gain a full outer shell, but instead of actually donating by losing or gaining electrons, what happens is them electrons are shared. Let's have a look at some examples of covalently bonded species. For example, ammonia is a good example of covalent bonding, and we're going to draw them dot and cross diagrams. Anytime we're looking at bonding, we need to draw them dot and cross. And sodium is in group 5, so it's going to have 5 electrons in its outer shell, and hydrogen is going to have 1 electron. That's all that hydrogen has. So if I draw the bonding, let's draw nitrogen first. I'm just going to draw its outer shell, and because it's in group 5, it's going to have 5 electrons in its outer shell. Currently, nitrogen has 5 electrons, but it wants to have 8. It wants to have a full outer shell, and the way it's going to achieve that is by covalently bonding. So there are 3 lone electrons and 1 pair of electrons up here. Now, what's going to happen is the hydrogen is actually going to want to gain a full outer shell as well, and the way that does that is it shares its electron, and also the nitrogen puts its electron in as well to make what is called a bonding pair. So I'm going to put the 3 electrons around these 3 lone electrons on the nitrogen to make them 3 bonding pairs. And now if we count up the electrons that are in the outer shell of the nitrogen, it's got 2, 4, 6, 8. So it is much, much happier. You can also represent these bonds with something called a ball and stick model. So I'll just draw out what that shows as well. So a ball and stick model is where you draw sticks to represent the bonds. This is actually what's called methane. And if I put the electrons in here, just show the electrons, then it looks like this. Every time there's a line, there is a pair of electrons, 1 electron from each species, unless you have 2 lines next to each other. What is shown by 2 lines? So for example, let's look at oxygen, which is double bonded. That just means that each oxygen is putting in 2 electrons into that bond. And in fact, you can get something called a triple bond, and in a triple bond, each puts in 3 electrons. So this is nitrogen, which triple bonds with itself, and that's what a triple bond looks like. Now, simple covalent species often have low melting and boiling points because of the fact that they have weak intermolecular forces. What that means is, for example, let's have a look at chlorine here and another chlorine here. They don't interact very much with each other, so it has a low melting point and a low boiling point. Remember when we looked at that ionic lattice, they were all attracting one another. Here the forces are really weak, so it has a low melting point and boiling point. And with these simple covalent structures, they can't conduct electricity as there's no charged particles in there to move around. But covalent species do not need to just be simple, they can be complex. And when we look at these giant covalent compounds, we are looking at what is called allotropes of carbon. And allotropes just means different forms of the same element. And all of these giant covalent compounds we're going to look at are allotropes of carbon, meaning they're made up of carbon. So let's have a look at some of these allotropes of carbon, and we will look at this bottom allotrope first. And this is in fact diamond, and you'll have all heard of diamond before, but maybe you haven't looked in detail at the bonding that occurs in diamond. So it is this giant covalent structure, and you can see that it makes up a lattice. All of these giant covalent compounds are lattices. They are large repeating units, as we looked at with them ionic compounds. But with diamond, the key thing is, if we look at one of the atoms in diamond, you can see that it has 4 bonds. And if you look at a carbon atom in its outer shell has 4 electrons. So that means that each electron in the outer shell of carbon is in a bonding pair. So there is 4 bonds going on with each carbon. But what does this mean for diamond structure and its properties? Because carbon is bonded 4 times and each electron is being used up inside a bond, it is incredibly strong because there's so many bonds inside this giant covalent structure. Also, because all the electrons are in bonding pairs, it will not conduct electricity ever because of the fact it has no free spare charges that can move around. And like with all of these giant covalent compounds we're going to have a look at, it has a really high melting and boiling point. All right, let's have a look at another form of carbon, and that is up here, this top right image, which is layers of graphite. And if you look at each individual atom of graphite, you will see that it's bonded 3 times. So the carbon is bonded 3 times. And if you look at that image of carbon, the atom which I've drawn here, the outer shell, you can see that if there is 3 bonding pairs, that means that 1 electron is not inside a bonding pair. And that's important to explaining some of the properties of graphite. Because one of the electrons is free, it does contain delocalized electrons, and because of these delocalized electrons, it will conduct electricity. As well as being able to conduct electricity, because of these delocalized electrons, they kind of sit in between the layers of graphite, and this means that it is a lubricant material. These layers can slide over one another. Now, graphite is incredibly strong in one direction. It's incredibly strong where there's these bonding pairs. However, between these layers, it's very weak due to these delocalized electrons, and therefore graphite is a fantastic lubricant, and it can be used in things like pencils because these layers just slide off one another. But graphite, just like diamond, it will have a high melting point and boiling point because of the fact that these covalent bonds between each atom are incredibly strong and take a lot of energy to break. The last giant covalent compound that we're going to have a look at is fullerenes. And fullerenes are kind of like a ball of graphite, really. Each carbon is still bonded 3 times. But this time they just make a ball-like structure, and in fact there is a specific type of fullerene that might come up in your exam, which is called a Buckminster fullerene or a buckyball, which has 60 carbons and is put into that spherical structure. And these fullerenes are like graphite. They have a lot of the same properties. They will conduct electricity. But their main function is the fact that they're used in delivering drugs around the body, because you can place the drug inside of that fullerene. Alright, we are on to our last type of bonding. We are going to look at metallic bonding, and then we're about halfway through the syllabus. So, metallic bonding, what is it all about? Well, in metallic bonding, you have positive ions, and you also have some delocalized electrons, these little red negative charges in your structure. And it's these delocalized electrons that control many of the properties of metallic bonding. One property is that they have great thermal and electrical conductivity. Just like with ionic bonding, because you've got 2 charged species, you've got these positive ions and these delocalized electrons, there is strong attraction. And this attraction, if you can remember what it was called, is electrostatic attraction. And this electrostatic attraction means that metals usually have a high melting and boiling point as well. Something you can do with these metals though is you can alter the properties a little bit to make it a better conductor or make it a little bit harder, and that's by introducing a different metal inside there, and I'll show you what I mean here. So here I've got a positive ion, maybe that's one metal like copper, and for example if I put another metal in, like tin, which is a bit bigger, and it kind of disrupts the structure of the metal. And this is called an alloy when you put a different metal inside another metal. And it alters the properties of that metal because of the fact that the layers are no longer perfectly uniform. They can no longer slide over one another. They're no longer malleable. That's another property of metals. They can bend without breaking. Well, if I put another metal inside there, it makes the structure a lot more rigid. And it also alters that melting point and boiling point as well. A couple of good examples of alloys are bronze and steel. You've probably heard of steel. Steel is an incredibly strong material that we use to build a lot of our houses and shopping centres from. Alright, we are about halfway through the video, so really well done for getting to this far in the video. If you'd like to grab yourself a quick cup of tea, maybe this would be a really good time to do that. But if you are groovy, then we will keep on moving through, and we are going to look at C4 quantitative chemistry next, and we are going to look at moles. Now, a lot of students ask me when we're doing quantitative chemistry, what is the point of scientists using moles as a unit? And the reason for it is because atoms are incredibly small, and using moles allows us to calculate the number of atoms that we are working with in chemistry. And it's incredibly useful for scientists because they can work out how much of a yield of a reaction they might get by using this formula. So the formula to work out moles is you can work it out by doing the mass of a substance that you have divided by the relative formula mass of that compound. Working out the relative formula mass of a compound sounds tricky, but it's not. It's just using the atomic masses from the periodic table. So here I've got carbon and here I have oxygen, and they both have atomic masses. Carbon's atomic mass is 12 and oxygen's is 16. So if I wanted to calculate the RFM of carbon dioxide, all I would do is 12 plus, and now there's 2 oxygens because that's what this little 2 is representing. So 12 plus 16 plus 16. So carbon dioxide's relative formula mass is 44, and the units for relative formula mass are atomic mass units or grams per mole. Either is completely fine. Now we know how to calculate the RFM. We could work out a question like this: how many moles are there in 22 grams of carbon dioxide? And we could just use this equation: moles equals mass, which is 22 grams, over the RFM of carbon dioxide, which is 44 grams per mole, and that gives you 0.5 moles. You can always rearrange the equation as well. You could calculate the mass if you know the moles. For example, if we wanted to calculate the mass of 5 moles of carbon dioxide, we could do that, because do you remember how to use these calculation triangles from physics? All you need to do is cover up the one that you want to calculate. So in this circumstance it's mass, so we cover up mass, and mass equals the moles times the RFM. So in 5 moles of carbon dioxide, it would just be 5 times 44 grams per mole, and that equals 220 grams. We can work out the ratio of moles of reactant to product by balancing equations. And this is something that students sometimes struggle with. So I'm going to go through the way that I balance an equation. And if you dig it, then that's really cool. If maybe you do it a different way, that's completely fine as well. But I'm going to show you how I do it. And I think it's a really good way of balancing equations. So the first thing I do is I draw a line down the center where the arrow is. And then I count up all of the atoms that I have on each side of the equation. So I have hydrogen, I have sulfur, I have oxygen, and I also have potassium. Now, what I then do is I count up the numbers that I have on each side. So I have 2 hydrogens here. I also have a hydrogen here. So in total, I have 3 hydrogens on this side of my reaction. My sulfurs, I've only got 1 sulfur on this side of the equation, and I have 5 oxygens. In terms of potassium, I only have 1. And then I do exactly the same on this side of my reaction as well. So I'm going to always have the same elements on each side. Never in a reaction will you have different. And let's count up what I have this time. So this side of the equation, I only have 2 hydrogens. I have 1 sulfur. I have 5 oxygens. And this time I have 2 potassiums. Now with these equations, it can sometimes be a bit of trial and error, but the way I always do it is I always balance the metals first, and I save oxygen and hydrogen till the end of every single equation. So firstly, let's try and balance our potassium, because clearly we don't have the same amount of potassium on both sides of my reaction. I have 2 on my right hand side and only 1 on my left hand side of my reaction. So I'm going to put a 2 in front. I can't put a 2 directly after my potassium. That doesn't work, okay? You can't put numbers there. That would change the compound you have. You can only put them at the start of a compound. So that means that I have 2 potassiums now on this side, and I've also changed the number of oxygens and hydrogens as well by doing that. So now on this side of my equation, I have 4 hydrogens, and I have now 6 oxygens. Maybe you can see how to finish off this equation now, but if you can't, don't worry, I'm going to go through it with you. So I said then I go to the next elements, which isn't oxygen and hydrogen. Look over, and sulfur is balanced already, so I don't really need to do anything with the numbers of sulfur. But I will do my oxygens and hydrogens now then. So on the left hand side of my reaction, I have 6 oxygens and 4 hydrogens, whereas on my right hand side, I only have 2 hydrogens and 5 oxygens. So I need to do something about that. And the way I'm going to do that is I'm going to put a 2 here in front of my H2O. I don't want to modify my number of potassiums or sulfurs, because that will throw the rest of my reaction off. So I'm going to put the 2 there. Now I have 4 hydrogens. Hopefully you can see that 2 times 2 is 4, and I now have 6 oxygens on this side, and you can see the numbers balance up, and that means I have a balanced reaction. Now we can balance equations. We can look at how we can apply that in chemistry in working out theoretical yields of reaction, which is really important to scientists. They can look at how much reactant is needed to make how much product, which is obviously incredibly important in industry for a number of different reasons. So let's look at this question and how we are going to work it out. It says, what mass of iron can be made if 3.2 grams of iron oxide is reacted with an excess amount of carbon? What it means by an excess amount of carbon is that you add more than is just needed for the reaction. This means that the iron oxide can be called what is a limiting reagent. This means that this amount is limiting how much product we are making. Now, we learned how to balance equations, but these numbers in front of our reagents are incredibly important, as these are the ratios that we have between each reagent. So I've got 2 iron oxide for every 3 carbon, to every 4 iron, to every 3 carbon dioxide. So if we have a look at the iron oxide to iron, because that's what's important for this question, for every 2 moles of iron oxide I will make 4 moles of iron, which is going to be incredibly important for this question. So the first thing that I need to do is I need to actually calculate how much moles of iron oxide I have in this question. And for that, I need to work out the RFM of iron oxide and use that moles equation of moles equals mass divided by RFM. And you can see I've worked out the RFM of iron oxide here. And the way I did that was I just looked at the periodic table, and iron has a relative atomic mass of 56, oxygen has 16. So I did 16 times 3 plus 56 times 2, and that equaled 160. So to work out my moles of iron oxide, all I need to do is I need to do 3.2 grams divided by 160 grams per mole. And that gives me an answer of 0.02 moles. Now, if I look at my ratios up here, if I have 0.02 moles of iron oxide, that means that I'll have 0.04 moles of iron being made because they're in a 1 to 2 ratio or 2 to 4 ratio. 2 to 4 is the same as 1 to 2. So all I need to do is moles of iron equals 0.02 moles times by 2, which is 0.04. Now, in order to calculate my mass of iron, I just need to rearrange my equation here, and this time I need to do mass equals moles times RFM. Now, I said earlier that the RFM, the RAM, the relative atomic mass, it's on its own, is 56 for iron. So all I need to do is 0.04 times by 56, and that will give me my answer. And that equals 2.24 grams. The next really small bit of this topic looks at concentration. And here at the top of the picture, I have 3 different concentrations of what looks a bit like orange squash. And here we have the most concentrated solution. And over here, we have what looks like a really dilute solution. That's what word we use to describe something that's not very concentrated. And how we work out the concentration in chemistry is we do the mass divided by the volume. Sometimes you can do the moles divided by the volume. It just depends on what units you are trying to get out of a question maybe that you get in an exam. Another key thing that we need to know is how to convert between different units, and volume sometimes is measured in centimeters cubed and sometimes decimeters cubed. And the way to convert between the two is, if you want to convert between centimeters cubed and decimeter cubed, all you need to do is divide by 1,000. And if you would like to convert from decimeters cubed to centimeters cubed, you would times by 1,000. To rearrange to calculate other parameters, all you need to do is cover up the bit of the triangle that you want to calculate. So I said that concentration is equal to the mass or the moles divided by the volume. But you could also calculate the volume or the mass using this triangle. So for example, if you wanted to calculate the mass or the moles, you could do the concentration times by the volume. So the way I use these triangles is I cover up what I want to calculate. So I'll show you with the volume. So if I want to calculate volume, I cover up volume, and that is mass divided by concentration. The top bit, the line on top, is like a divide sign, and next to is a times. So volume is mass divided by concentration. And that is all the maths in chemistry topic, really. What we're going to go on and look at now is we're going to look at different types of reactions. This next topic is called chemical changes, and the first bit of the topic looks at which metals are most reactive. And the way we work out this reactivity series is either by reacting these metals with water or with acid and seeing which ones have the most vigorous reactions. You can just put a little bit of the metal inside a little bit of acid or water, and when you do this, this is going to make hydrogen gas, and the ones which make the most hydrogen gas in the smallest amount of time, we can say that that is the most reactive. And over here I do have the reactivity series with, at the top, the most reactive, and at the bottom we have the least reactive. I've also put hydrogen and carbon into my reactivity series, and it's going to become apparent when we look at how we extract metals why I've included hydrogen and carbon in my reactivity series. And I've also put here a mnemonic, for how you could remember the reactivity series, because you might be asked why which metal is more reactive, and you need to know which one is. So you do need to remember the order of this reactivity series. And you can also test the reactivity using displacement reactions. And we looked at displacement reactions with halogens, and the same kind of thing occurs with these metals. You can use a more reactive metal to displace a less reactive metal from a compound. And I'll show you an example of that. You could have potassium and react it with something really unreactive, maybe like silver nitrate. Silver is an incredibly unreactive metal, and what's going to happen is the potassium is going to come along and steal the nitrate away. So you're going to get potassium nitrate plus silver, and you could definitely see that reaction had happened with this, because you'd notice that silver would start to come out and be a precipitate of this reaction. And these reactions only work because potassium is more reactive than silver, so we'll steal its nitrate away from it. Remember that all chemicals want to be bonded, and this is why they do these displacement reactions. Getting into the higher levels of this, what's actually going on with the individual atoms in this? Well, the potassium is going from an oxidation state of 0, and it's going to actually lose electrons to become potassium plus, and that's why it's more reactive, is because it's better at losing a electron than the silver is. And losing electrons is called oxidation. And you can remember that oxidation is losing electrons with the mnemonic oil rig, which is oxidation is loss, reduction is gain. Now, we use these displacement reactions in industry to collect important metals that we need in everyday life, because metals are not often found pure. Now, when we find a metal and it's not pure, we usually call this an ore, and that just means that it contains a metal with impurities. An example would be iron oxide. Iron oxide is a metal that we dig up from the ground, but we need to get rid of the oxygen from the iron oxide. And the way we do that, and the reason why I included carbon in this table, is because we can react it with carbon. Now, carbon is more reactive than iron, you can see on this reactivity series. So when I react it with the carbon steals the oxygen in a displacement reaction, and that makes carbon dioxide, and it also makes iron. These are incredibly important reactions as we need them for everyday life. Iron is an incredibly important metal that we need for making steel and other objects like that. Now, using carbon isn't as desirable as using hydrogen to extract metals. We can use hydrogen to extract copper, for example, if copper is bonded to oxygen, but we couldn't use hydrogen with iron because hydrogen is not as reactive. If we look at copper oxide and we react that with hydrogen, our products of that are the hydrogen's more reactive, so it steals the oxygen, and hydrogen and oxygen make water. And copper is my other product. And that's a lot more desirable, as carbon dioxide is a greenhouse gas, so we'd prefer not to emit it, but sometimes we have to because carbon is the only thing that is more reactive. What about these metals up here that are a lot more reactive than carbon? What do we use for them? Well, we use a technique called electrolysis, and we're going to look and see how electrolysis works a little bit later on. There's a few more reactions we need to know in this topic, as well as displacement reactions, and they are what happens if I react metal with an acid, or a acid with an alkali, or a acid with a metal carbonate. And you just need to know the products that we will make. And there's a few rules outlined on this slide for naming some of these products. especially the salt, because this is the hardest thing to remember. And it depends about what acid you use to which salt you are going to make. So let's have a look at a few examples. Let's take a metal, for example, like sodium, and we will react it with some sulfuric acid. Now, what products are we going to make from this reaction? Well, it says we're going to make a salt and we're also going to make some hydrogen. So how do I name this salt? Well, I look at this table and I decide which acid I use. So I use sulfuric acid. So I'm going to make the metal sulfate. So I'm going to make sodium sulfate. And my other product of the reaction is hydrogen, which is quite easy. Now let's have a look at another reaction now. An acid and an alkali make salt and water. So let's pick our acid. This time we'll take a different one. So we'll use phosphoric acid and we will add our alkali to it, which is usually a metal hydroxide. So lithium hydroxide. Now what an alkali is just a soluble base. That means that it is a base which will dissolve in water. And I'm going to make a salt, which will be the metal, and then we use that table again, which will be lithium phosphate, and my other product is water. And then finally, let's look at an example down here. An acid plus a metal carbonate makes salt, water, and carbon dioxide. So let's pick another different type of acid. This time we'll pick hydrochloric acid. We'll add our metal carbonate. We'll pick copper carbonate. Doesn't matter which one we pick. We're always going to make a salt, water, and carbon dioxide. So naming my salt, I looked at that table again. With hydrochloric acid, I make copper chloride. Water. And carbon dioxide. Lovely. With these acids, we also need to know what is the difference between a strong and a weak acid, which we will look at now. And this kind of slide summarizes it all up. I'll just talk really quickly on what I'm actually saying here. A strong acid is something that is fully dissociated. And what that means is when we dissolve it in water, so we've got some hydrochloric acid here, when I dissolve it in water, I fully make all the hydrogen ions. With a weak acid, like this one here, which is actually called ethanoic acid, I only get partial dissociation. This here is a reversible reaction, which you actually do a lot of in paper 2. You'll look at reversible reactions. And it doesn't fully dissociate, so I don't make only H plus ions. The reaction can actually go backwards and make the original reactant. I can still dilute strong acids though to make them a higher pH, and I can do that by changing the hydrogen ion concentration in my solution. Now here it says lists all the different pHs and the hydrogen ion concentration. That's what these are, they're H plus concentrations. So anything that has a pH of 1 has a hydrogen ion concentration of 1 times 10 to the minus 1. So if I wanted to turn that into a pH 2 solution, all I would need to do is add an extra 10 centimeters cubed of water. If I wanted to add turn it into a pH 3, I would add 100, and I'd keep going up by a factor of 10 each time I want to get the pH up by 1. Now I said we'd look at electrolysis a little bit later on, and now we are on to electrolysis. And electrolysis is a great way of separating ionic compounds. Now with these ionic compounds, they need to be either molten or aqueous solutions. This is because of the fact those ions need to be able to move. So once I have my aqueous or molten solution, let's for this example say that we have a molten solution of lead bromide. So in there I've got some Pb2 plus ions, and I also have some Br minus ions. what else do I have rocking in here? Well, I have an anode and a cathode. And the way to remember which one's positive and which one's negative is to remember to not panic. The positive is the anode and the negative is the cathode. So my positive electrode is my anode. So this one's here is positive. My negative one is my cathode. All right, so what is going on in this electrolysis? I have a power supply up here, and I now have two electrodes here with charges on them. And these electrodes are usually made out of graphite or carbon because they need to be really good conductors. And we looked at why graphite was such a good conductor earlier in this video. So now they're charged, what they're going to do is they're going to attract the ions to them. Remember, opposites attract in electrolysis. So the positive ions are going to move to the cathode and the negative ions are going to move to the anode. And this just separates ionic substances. And that's what electrolysis is. It's the separation of ionic substances. And then what goes on at the anode and the cathode is oxidation and reduction. Remember oil rig for this. It's very important. So the bromide ions go towards the anode, and what actually goes on is because they're negatively charged, they've gained electrons. Well, they lose these electrons at the anode, and loss of electrons, well, that is oxidation. And at the cathode, what is going on? Well, I have these Pb2 plus ions, and they are going to gain them electrons, and that is called reduction. With a molten electrolysis, you always make the ions that we started with. Aqueous electrolysis are a little bit more complicated, and that is what we're going to look at now. What products we actually make from an aqueous electrolysis. So when you have your ionic compound and you dissolve it in solution, you are also adding in H plus ions from the water, and you are also adding in OH minus ions from that water as well. And the OH minus is going to be attracted to the positive anode, and the H plus is going to be attracted to the negative cathode. And deciding whether you're going to make oxygen as a product at the anode depends on whether there are halogens in your solution. If the negative ions are halogens, then you will always make the halogen. So for example, if you have chloride, iodide, bromide, you will make chlorine, iodine, or bromine at your anode. However, if the negative ions are not halogens, for example, they are sulfate or carbonate, or even sulfide, then you will always make oxygen will be your product. You don't need to know why this is, you just need to know that that is the case. Now at the cathode, if the positive ions are less reactive than hydrogen, that is what you are going to make. So for example, if you've got lead, which is incredibly unreactive, or silver, or gold, then that is what you will make at your cathode. However, if your positive ions are very reactive, for example, if you've got something like sodium or you've got potassium, you will make hydrogen at this electrode. Let's have a look at what I actually mean. So let's have a look at some products that I might make from an electrolysis. Here I have an electrolysis of calcium sulfate. If I'm doing a molten electrolysis, my products are just going to simply be calcium, and I'm going to also make sulfur dioxide. However, with my aqueous, I'm going to make different products, aren't I? I'm going to not make calcium because calcium is quite a reactive metal. So instead, I'm going to make hydrogen, and I'm going to also make, because of the fact that sulfate isn't a halogen, I'm going to make oxygen. So you can see that the products of my electrolysis are completely different because of the fact that I am doing it in water and I'm adding different ions inside there. All right, we are on the home straight, people. We are on that last topic, which is energy changes. And the reason why we get energy changes in a reaction is because of the fact when bonds are broken or being made, our reaction can give out energy to the surroundings or take in some energy. Now, if my surroundings get hotter, if the heat goes up, then we say our reaction is exothermic. If our heat goes down, then we can say that our reaction is endothermic. And I like to remember it as exothermic is heat exiting and endothermic is heat entering. So let's look at a reaction profile which can explain what energy changes are actually happening in our reaction. And let's look at an exothermic one first. In an exothermic reaction, the energy of our reactants are a lot higher than the energy of our products. And this is the reason why that heat is given out into the surroundings. And you can quantify it by measuring the gap between them two. And you might be asking, well, why is there a bit of a lump here at the start? This is called our activation energy. This is the minimum energy needed to start our reaction. And if I now look at a endothermic reaction profile, the energy of my reactants is lower than our products. That is why it takes in energy from the surroundings, and the amount of energy is that gap, and it still has the activation energy here, sometimes represented with a big E and a little a. You can track whether a reaction is exothermic or endothermic by simply putting a thermometer inside a reaction mixture, and is exothermic if the temp goes up, and it is endothermic if the temp goes down. Now, you can actually see in my required practical videos all of the little details you need to know about these practicals in that, so I'm not going to go into it in much detail at all. But we also need to know some important uses of exothermic and endothermic reactions. And endothermic reactions are incredibly important in some household appliances like a cool pack. If you get a sports injury, you'll often grab a cool pack, and when you squeeze that cool pack, you're starting an endothermic reaction, and that is why it gets really cold, and then you apply it to the area of your body which you are injured. Exothermic reactions, anything which is combustion, is an example of a exothermic reaction. And they've tried to exploit some exothermic reactions in examples like self-heating cans, where you can heat up your food using a reaction rather than using a gas cooker or an electric cooker. This means you could eat your tin of beans on the go. How cool does that sound? Maybe a little bit dangerous though, because a lot of the time toxic chemicals are being used in these self-heating cans, and you cannot control, you can't turn it off once you've started that heating process. You can work out whether a reaction is exothermic or endothermic by calculating the bond enthalpy of your reaction. And generally what you can say is forming bonds is exothermic and breaking bonds is endothermic. So if it requires more energy to break the bonds, then it is endothermic, and if it requires more energy to form the bonds, then it is an exothermic process. So let's have a look at which one requires more energy, and the way you're going to do that is by calculating the energy required to break all of these bonds first, and then form all of these bonds second. So what is going on with the breaking? Let's have a look. So I've got 4 CH bonds, so that's going to be 4 times CH on the table is 413 kilojoules per mole. And I'm also going to add it to there's 2 bonds here, which I'm going to have to break as well. So 2 times my OO, which is 498 kilojoules per mole. And if I add them together, I get 2,648 kilojoules per mole. Now, if I look at my forming bonds on this side of my reaction, I have 4 CO bonds. You can see there when I break them. Sometimes it's easier to draw out the bonds like I have when you get a question like this, because it will help you calculate how many of each bonds you've got. So that's 1,079 kilojoules per mole for each of them. And I'm going to add it to 4 times OH. There's 4 of them. And that equals 6,172 kilojoules per mole. So here you can see that forming bonds is more energy, so therefore our reaction is exothermic. And you'd actually expect this because it is a combustion reaction, but I do have an exothermic reaction. And you could quantify how much exothermic it is by doing a takeaway of one another. And 2648 minus 6,172 is minus 3,524 kilojoules per mole. And that's how exothermic this reaction is. We have in fact reached the end of the video now. Well done, you have absolutely smashed it. Well done for getting through the end of the video. If you did like it, please remember to like the video and subscribe to the channel. If you didn't understand anything, like I said at the beginning, please check in my playlists. Go into chemistry, look through the topics, find the individual topics. I go through them in a lot more detail in that. This is just a real quick overview, and I hope you did enjoy it, and I hope you got something from it, because I really enjoy making these videos and hopefully helping you people out.